Let's get started. The intent of this video is to review the external features on the B-17 Flying Fortress. What we'll do is we'll start at the nose of the airplane, walk around the lower lobe area, and then look at some features in the upper lobe per this view. We're going to be looking at the port side, which is the left side of the airplane. Just standard naming convention, the port side's the left side, starboard's the right side. And one way to remember that is port and left both have 4 letters. This is if you're facing forward on the ship or the airplane. You always board a commercial airplane on the port side. Your seat assignment, A, B, C, D. A is always on the port side. And engine numbering convention starts on the port side. So this would be engine 1, that's engine 2, and then 3 and 4 are on the opposite side. So starting at the nose, we see a fairing. There's actually an antenna underneath this fairing. It looks like a football, and that's the ADF loop antenna. So ADF is short for Aerial Directional Finder Antenna, and it's one of the 4 ways that our Navigator, and that's the Navigator's window right here, that our Navigator uses to determine the position of the airplane relative to Earth. So if we're coming back to Great Britain from a mission, and at Great Britain, they've set up a localizer beam, a radio beam, and we just basically use this antenna to follow the strongest signal. So that's one of his ways of navigating. He has a flexible mount, which you can see out of this window. All of the machine guns on the B-17 are Browning M2 50 caliber machine guns. The ammo amount varies on location. I think he has about 250 rounds, where our waist gunner have something like 500 rounds. So he has his own machine gun, which he would use to protect this part of the airplane. If we move further aft, we don't see it, but there is actually the forward crew entry hatch. So it's a hinged door. They would open it up, and then they can ingress into the airplane in the forward cavity here. If we move farther aft, we can see a little bit of the main gear wheel that is exposed. So in flight, this is intentional. They wanted the wheel to be protruding below the engine nacelle. And the reason for that is that if you have a wheels up landing, say the gear doesn't articulate down in the down and lock position, then this wheel and tire will take some of the ground load, some of the flotation load, and transfer that into the engine number 2 and 3 nacelle. So this is a design feature for redundancy. If we move further aft, we can see, well, obviously we have our engines here. Those are Wright Curtis Cyclone 1820-97 engines, each producing 1,200 horsepower. And in order to maintain that horsepower from sea level up to their combat altitude, which would be maximum about 30,000 feet, you need to compress the air, and that's why we have these turbochargers down here to perform that function. If we move further aft, as we see the connection from the wing into the fuselage, and this is called the wing root area, we see a little tube sticking out about 4 to 6 inches long, and that is the crew relief tube. So if a crew member, there's a crew of 10, if any of the crew members needed to relieve themselves, number 1, they would decouple themselves from their station. When I say decouple, they are tethered by 3 systems. You have an oxygen system, you have a comm system, you have a throat mic and a headset, and then you had your heated suit electrical line going into a rheostat. So you would unplug all that to make your way around the airplane. Now, the problem with the oxygen system, since every crew member is essentially on life support, uncoupling yourself from that oxygen system, you've got about 60 seconds before anoxia hits and you pass out. You'll die in about 20 minutes at 30,000 feet without mechanically fed oxygen. So the crew members at their stations would grab what's called a walk-around bottle. We'll do a whole section on oxygen later. It's about the size of a pineapple. So you would just take your oxygen hose and tap into that. You get about 8 minutes worth of oxygen. You'd generally clip that to your flak jacket or your parachute harness, and you could walk around. So you'd make your way here, do your business. Now, before you do your business, you're going to inform the ball turret gunner. This is important because the spray coming out the end of this hose could get on his transparencies and freeze up. And if it ices up, then that'll lose his visibility. So he'll go ahead and rotate his guns aft, like in this position, while you do your business, and then he'll go back to his scanning position. If we move further aft, we see a little pipe with a weight on the end of it, and that is a trailing wire antenna, and a blow-up view of that is down here. So this is a 3-pound weight. It's got a wire connected to it that you can spool out at 200 feet. And the radio room operator, who's over here, he would use that for long-range communications. The pilot would always make sure he talks to the radio room operator before they land and make sure that he's spooled that in. Otherwise, the weight will bounce around and the wire could damage the aft section of the airplane. We have 2 waist gunners. We have one on the port side, like we see here, the left side, and then another one on the starboard side. The arc travel is pretty good with these guns, although if you move them forward, you can't shoot the wing. There's a mechanical stop here, so that'll keep you from hitting your wingtip. Now this actually has a window. The F models would just had an opened up window, an opened up cavity. It didn't have any plexiglass or anything. So this is a little bit different design. If we move further aft, we'll see an arrow pointing to the bottom part of the fuselage, and that's where the tail wheel stows. So we call these tail draggers because we have 3 points of contact. You have your main gear, and then you have your tail wheel. While the airplane's on the ground, you'll have a 10-degree slope, by the way, of the airplane. And pilots were instructed when the airplane takes off, you want to do a 3-point liftoff. In other words, you're going to be going down the runway. Don't lift your tail up and then lift off from your main gear. You want to lift off from your tail wheel and your wheels at the same time, because that 10-degree slope is actually optimized for this wing for maximum lift and minimum drag. So in movies or documentaries, you might see some other airplanes where they're going down the runway, they lift the tail up and then they take off, but not on the B-17. This surface is called the horizontal stabilizer, and it's somewhat unique in that it is a symmetrical airfoil. So what that means is the curvature on the upper surface matches the curvature on the lower surface. So curvature is called camber. So we call it a camberless airfoil. Most airplanes, like if you take the 757, you would actually have let's talk about the wing first. So to generate lift on a subsonic airplane, you want a positive cambered airfoil. So if we were to take a cross-section of this wing, you'd find a flat lower surface and a curved upper surface, and that generates lift. Now, the center of the gravity of the entire airplane is going to be forward of that. So I'll just exaggerate it. The lift vector is generally at the cord-to-cord location, so say right about here-ish. And then the center of gravity of the entire airplane is going to be forward of that. So that's pointing down. Now, to maintain a longitudinally statically stable airplane, just because of the distance between those two vectors, you want a down tail load. That's what you want. So if you take this, I'll use a 757, you would have a negative cambered horizontal stabilizer. So you'd find a flat upper surface and a curved lower surface. And you have a down tail load that equates to about 3 to 5% of the airplane weight. And the reason they do this is so that you can maintain stability in case you have a stall. So if you point the nose of the airplane up enough, your boundary layer on the upper wing surface will separate and the airplane will start to stall. But you want it to be able to recover back into this state. So having that down tail load, given the vectors and the forces in flight, allows that. So since we don't have a down tail load, that means that we have to have a down tail load. Since we don't have a down tail load due to negative camber, we have to have a down tail load either through angle of attack or using the elevator. So the pilot can trim out the elevator to get that down tail load. And the reason why they made these symmetrical is that they're interchangeable. So you can take the horizontal stabilizer from the left side, unbolt it, and put it on the right side. Of course, the color scheme would have to be repainted if they do that. If we move further aft, we will see the tail gunner's position. He's in the kneeling position. He's sitting on a bicycle seat made by Schwinn. That's his little 35 mil rad gun sight that's mechanically linked to his twin 50 caliber machine guns. And he has a little bit of ballistic glass right here, about 2 inches thick. There's only 2 locations that have ballistic armor, glass anyway, transparencies, one here and the flight deck. None of this is ballistic, nor the upper turret, nor any of this here. Okay, moving to the top now. We see the rudder. Rudder gives yaw control of the airplane, and that's called the rudder tab. So we'd use that to help trim out the rudder if we had any asymmetric thrust yaw that we couldn't correct otherwise. All of the control surfaces on the B-17 are doped fabric, which means that the rudder, aileron, this guy here on the end of the wing, gives you roll control, and then the elevator we talked about earlier that gives you pitch control. Those are all fabric, and fabric covered control surfaces are lighter, better battle damage resistant, and they just work. So they're easy to repair. None of the control surfaces, by the way, are power assist. So the mechanical might of the pilot co-pilot and the mechanical advantage to each one of these surfaces are what moves it. If we move forward, we'll see this big fairing. So I'm outlining it right here. And that's called the dorsal fin. The dorsal fin, there's nothing in here, it's empty. It's used to transition the air load as it scrubs along the crown of the fuselage and it transitions into the vertical stabilizer. It's there to minimize drag, essentially. The dorsal fin was added on the E series or E models of the B-17. So if you look at the earlier B, C, and D, in this graphic you can see the shark fin assembly. So you don't have that nice gradual transition. And that's one way to tell the earlier versions of the B-17 to the later versions, is looking for the dorsal fin. If we move farther forward, we can see where the radio shack is. This is a radio room operator. He has a hatch that he could decouple, and then he just lays it on the floor, and then he's got a yoke, and he can bring a 50 caliber machine gun out to protect this part of the airplane. If we move farther forward, we see the outline for where the life rafts are stowed. There's 2 life rafts. Inside the radio room, there's these handles he can pull, which would jettison these doors, and then the life rafts can be accessible if we have a ditching situation. Moving forward, further forward, we see the top turret, and that's the flight engineer. He has dual responsibility, as does the radio room operator, and he's responsible for since he's a flight engineer, he mainly does the fuel management and help the pilot co-pilot by calling out airspeeds and other parameters that are significant. He would be a staff sergeant. If we move forward, we can see the compartment of the pilot co-pilot, and I mentioned that just the windscreen is armored, about 2-inch thick ballistic glass. Should be able to stop a 30 caliber slug. We move farther forward and we see a celestial navigation dome. Now the Navigator has 4 ways of navigating. We talked about one, the aerial directional finder. The other, the other one that we're going to talk about is celestial navigation. So if you could pull out a sextant, you would poke your head in here and take position of the sun or stars at 2 different times, look up charts, and that can tell you your position relative to the Earth. You'd be within about 25 miles. So you would use that, say, as a backup. And that's the same navigation method that ships would use. If we move farther forward, we can see the bombardier's crew position. He sits in a chair and actually faces forward. And most of the time on the bomb run, he's hunched over this instrument called the Norton bomb sight. And we'll do a whole video on the Norton bomb sight. None of this transparency is armored. It's just plexiglass, and he's got some tempered glass right up front. Now, if we take a look at the airplane in general, it's aluminum. The material, it's 24ST, it's alclad. So there's a modern equivalent to that. We would say that this is it's a copper-based 2024 T4 temper. So it's a naturally aged aluminum. And when we say clad, so you have clad, you have bare. Clad just gives you better corrosion resistance. They roll bond on a little bit of pure aluminum onto the load-bearing, heat-treated material. And that gives you corrosion protection. And it's also very shiny. So sometimes they didn't paint these airplanes. You see them shiny. That's the clad that you can polish. So, okay, if there's any questions you have, let me know in the comment section. Also, if there's any particular topics you would like on bombing in World War II, let me know. I'm just starting this channel and appreciate any comments. Thank you very much.